All right, we're officially on the last section for this course. Unfortunately, this will be in two videos. This first part, we are going to talk about solving exponential equations. We looked at some basic ones, and in this one, we're going to get into some more complex exponential equations. So to start off with, let's talk about the two things that we're going to use when we talk about solving exponential equations. The first one we have is the principle of exponential equality. All right, that's a really fancy way of just saying that if we have the same bases, then our exponents have to be equal. The second one we have is the principle of logarithmic equality. And basically, for both of these, we're just taking advantage of the fact that exponentials and logarithms are one-to-one. And what we're going to do with the principle of logarithmic equality is if we have an equation, we can take the log of both sides, and it is still a true statement. All right, so those are going to be the two things that we play around with. This is going to be our procedure. The first one that we want to attempt, there's going to be two different types of problems that we have here. The first one that we want to do is we want to try rewriting the equation with the same bases. If we can do this, then we can use the principle of exponential equality. We can cancel the bases and solve the resulting equation. Now, the second one is if you cannot rewrite the equation with same bases, then what we want to do is we want to start by isolating the exponential. We want to move all terms outside of the exponential to the other side. We can take the logarithm of both sides, and the only thing is make sure we're taking the same logarithm. We've got two that we can work with in our calculator. We have the common log, and we have the natural log. And as long as you take the same log of both sides, then you're okay. From there, after we take the log of both sides, then we're going to use some of the techniques that we talked about in the last section. We can move the exponent to the front, turn it into a coefficient. And after our variable is out of the exponent, then we can go ahead and just solve the resulting equation. One of the things to note is don't get so worried about, logs of things. Remember that these are essentially just numbers. If you have the logarithm of a number, it is just a constant. It is just a number. And we want to treat it just like we would any other constant term or coefficient. We can still add them, subtract them, divide them, and then keep going. Okay? For procedure 2, just note that we are going to be using our calculators in order to finish solving these if we are asked to approximate the answer. Finally, the last thing that I do want to point out is because exponential equations have a domain of all real numbers, the check step is not required. It is recommended, but it is not required. All right, so that's what we're going to be working with in this particular video. So let's go ahead and jump into some examples. All right, we're going to start off relatively easy. The first one that we have is we have 10 to the x plus 2 equals 10 to the 3x. And for this one, we can go ahead and use our property of exponential equality. We do have our bases are the same, and so we can go ahead and cancel them and solve the resulting equation. And so our resulting equation, what we get is x plus 2 equals 3x. This is now a linear equation, and so we can go ahead and finish solving this. We want all of our variables on one side. We want all of our constants on the other. So I can subtract x from the left. If we do that, our x's cancel. We are just left with a 2. And on the right side, if we do 3x minus x, we get 2x. And finally, we divide by the coefficient, and we get x equals 1. And we're done. All right, let's look at a couple other ones. All right, if we come to example B, the first thing that we need to do is we do need to isolate our exponential. And so in order to do this, we're basically just going to move everything outside of our exponential. Our exponential is the 1.2 raised to the x. And so we want to get rid of everything else from there. So we basically used our linear techniques. So we're going to subtract 1. We get 25. I still have the 5 on the outside. This is 5 times 1.2 raised to the x. And so we can divide by 5. And now we have our exponential is isolated. All right, we cannot write these with the same base. And so what we need to do is we do need to go ahead and take the log of both sides. And so if we take the log of both sides, again, it just has to be the same log. So I'm going to do common log. And after we take the log of both sides, what this allows us to do is use our power property, and we can bring our variable out of the exponent and move it to the front. Again, remember, don't worry so much about what log of 1.2 is. It is just a number. And what we have here is we have x times a number equals another number. Just like we did in our previous example, well, to get x by itself, we need to divide by that number. So we're going to divide both sides by log of 1.2. And this is now a calculator problem. So this is the exact answer. Make sure that when you're working on your homework, you check what does it want. Our exact answer is log of 5 divided by log of 1.2. And then we want to probably approximate it, which is going to be a calculator problem. All right, when I do this in my calculator, I get 8.827. And so that is our approximate answer. Now, one of the things I do want to point out is if we come back to this step, if you recall, when we converted from logarithmic to exponential, remember that what we had was b to the c equals x. Sorry, that was supposed to be a b to the c. Remember that we did our around the world thing. Okay, well, if we want to go backwards using this statement that we have right here. Okay, we have our exponential. We're going to convert it into a logarithm. Okay, so the base is going to be the base. So this is 1.2. We have this number. on the other side, the 5 is going to become the number inside our logarithm, and the exponent becomes what's on the other side. Okay, I don't like doing this, but this is basically what we have. And the main thing I want to point out is this is where our change of base formula comes from. We can't do log of 1.2 of 5, but we can do log 5 divided by log of 1.2. And that's exactly what we did when we took the log of both sides, was we got log of 5 divided by log of 1.2. This is where our change of base formula comes in. All right, let's go ahead and look at some other examples and see what we can do. All right, we're going to come down to example C. Okay, we do have our exponential is isolated. And for this one, we cannot write them with the same bases. And so we do need to go ahead and take a log of both sides. All right, so if we take a log of both sides, what we get is log of 1/4 raised to the x minus 1 equals log of 1/9. All right, we can go ahead and move our x minus 1 to the front, and we do want to keep it inside parentheses. Remember again, log of 1/4, this is basically just a number. And there's two things that you can do with this. One of the things that you can do with this is you can go ahead and distribute it. And so what we get is x log of 1/4 minus log of 1/4 equals log of 1/9. All right, in order to solve for x, remember that these logs are just numbers. And so here, the next thing that I would want to do is solve my linear equation. I want to add my log of 1/4 to both sides. And then I want to get x by itself, so I'm going to divide by my log of 1/4. And this is what we can go ahead and plug into our calculator. And so what we have for our exact answer is log of 1/9 plus log of 1/4. Make sure that when you put this in that you have all of your parentheses where they need to be, including around the numerator. All right, let's plug this into our calculator and see what we come up with. Again, we do want parentheses and around that whole numerator. And when I plug this into my calculator, what I come up with is x equals 2.585. Okay, now, again, remember with these logarithms, there's lots of ways to do this. Okay, so let's talk about a couple other things that we could have done. Starting at this step, no, sorry, back up. Starting at this step, we could go a little bit different route. What we can do is, instead of distributing the log, I can divide by the log. What this allows us to do is we don't have to do that parenthesis, make sure that we have those parentheses in the numerator. And from there we can go ahead and just add 1 to both sides. If we do this, we get x equals log of 1/9 divided by log of 1/4. And then we just have to add 1 onto that result. And so if we go ahead and plug this into our calculator, we have log of 1/9 divided by log of 1/4 plus 1, and I get the same answer. I do still get 2.585. All right, that's another way that we could do this. There are also, I'm going to do one more, okay? If you don't like the fractions, okay, and I know a lot of us don't like fractions, there's one other thing that we could do, and just to show that it doesn't really matter. Okay, we can write, remember that we can always change a unit fraction into a whole number by making the exponent negative. So for instance, 1/4 is 4 to the negative 1, and we can go ahead and distribute that. Same thing with the 9. We can to the 1/9. We can write this as 9 to the negative 1. Alright, so what we get is 4 to the negative x plus 1 equals 9 to the negative 1. And we can still take the logarithm of both sides. If we do this, we get negative x plus 1. We do want that in parentheses. Log of 4. If you want, you can also move this negative 1 to the front because it is the exponent in a logarithm, and so we get negative log of 9. And then again from here, you can either distribute or you can divide. I'm going to go ahead and divide. We get negative x plus 1 equals negative log of 9 divided by log of 4. Again, we can subtract the 1 this time, and we get negative x equals negative log of 9 over log of 4 minus 1. And then if we divide by negative 1, we can change these signs, and what we get is log of 9 over log of 4 plus 1. Okay, and so here all I did was take this negative and apply it to each one of these terms. All right, if we go ahead and try this now, we get log of 9 divided by log of 4 plus 1, and I do still get the same answer. I do still get the 2.585. Okay, so just keep in mind, there's lots of things that you can do if you don't want to distribute, if you don't want these nasty fractions, if you don't want, to work with fractions from the beginning. You can always go ahead and use your rules of exponents and your properties of logarithms in order to make it a little bit easier. All right, let's go ahead and come over to example D. Example D, we don't have a whole lot of options on this one. So we are just going to go ahead and use our basic techniques. All right, I cannot write these numbers with the same base, and so we're not going to try. So what we're going to do is we're going to take logs of both sides. Now remember I said you can take log or you can take natural log, as long as you're doing the same thing. And for this one, because I do have this e right here, I'm going to make it a little bit easier on myself, and I'm going to take the natural log of both sides. On the left, I'm going to write it natural log. On the right, I'm going to use the other notation. I'm going to write it as log base e, and we have e to the 2x. All right, from here, we can go ahead and move our exponent down to the front. So we have x minus 3 in parentheses times natural log of 5 equals, and on the right side, my log base e and my e cancel, leaving me with just a 2x. For this one, in order to get the x's on, we have to combine the x's. We need to get our x's together. This one we do have to distribute because we have x's on both sides. So we're going to go ahead and distribute the natural log of 5. So we get x natural log of 5 minus 3 natural log of 5 equals 2x. All right, I want to get all of my x's together, so I'm going to move my x term here. Again, remember, natural log of 5 is just a number. We treat it just like all the other ones, and so we can go ahead and subtract this to the other side. What we have now is negative 3 natural log of 5 equals 2x minus x natural log of 5. We can't combine these because one of them is not a nice number. But now that we have all of our x's together, we can factor it out. And so if we factor out the x, we get 2 minus natural log of 5 on the inside. And on the left, we still have our negative 3 natural log of 5. We now have x times a number, and just like we do with all of our other equations, we can divide by that number. It's not a nice number, but it is still a number. And when we divide, what we get is x equals negative 3 natural log of 5 over 2 minus natural log of 5. That is our exact answer. If we want to approximate it, we do want to make sure that we put parentheses around that denominator. And when we do that, when we plug this into our calculator, what we should get is negative 12.362. And we're done. All right, let's go ahead and see. We got 2 more examples. Let's come down to example E. Example E, you can go ahead and take logs of both sides. But again, the first thing I always want to do is I want to see if I can rewrite this with same bases. We can't write 8 in terms of 4, but we can actually write both of these in terms of something else. 4 is equal to 2 squared. And so the left side, what we can do is rewrite this as 2 to the 2 times x plus 1. 8 is equal to 2 cubed. And so we can write this as 2 raised to the 3 times 2 minus x. And now that we have same bases, we can go ahead and cancel them. We can distribute to clear the parentheses. So we get 2x plus 2 equals 6 minus 3x. And we can finish solving. So this is just a linear equation again. And so we can go ahead and move our variables to one side. We can move our constants to the other. And what we get is 5x equals 4. And we can divide by the 5. And so we get a nice answer for this. We don't need a calculator for this one. We get x is equal to 4/5. All right, last one. Let's come over to example F. Okay, we have 9.5 times e raised to the 0.005x equals 19. First thing we want to do is we do want to isolate our exponential. And so I want to get rid of the 9.5. If we divide both sides by 9.5, we get e to the 0.005x is equal to 2. I cannot write these with same basis, so we are going to go ahead and take the log of both sides. And again, because this is base e, I want to do natural log. So on the left, I'm going to write this as log base e. On the right, I'm just going to write it as natural log. And now we can go ahead and cancel our log base e and our e, and we are left with 0.005x equals natural log of 2. We can then go ahead and divide by the coefficient. We want to divide by 0.005 to both sides. And what we get is 138.629. All right, those are our examples for solving basic exponential equations, okay? And now we are going to go ahead and apply this to a couple other things. All right, the next thing that we want to do is we want to talk about solving exponentials graphically, and then we're also going to do it algebraically. And so just a reminder, when we talk about solving graphically, we want to solve where is f of x equal to g of x. We are looking for the point of intersection, and we are looking at this point right here. And so here, what it looks like is x is equal to 2. We come down here. This is what we're looking for. All right, so now if we talk about solving this algebraically, okay, we want f of x equals g of x. Well, f of x is equal to e to the x. g of x is equal to 7.5. And now we want to go ahead and solve this. In order to solve this, I want to get x out of the exponent, which means I need to take the log of both sides. And I'm going to go ahead and use natural log again, because we have the e. On the left, I'm going to write it as log base e, and on the right, I'm going to write it as natural log. On the left, we can cancel our bases, our log base and our base for our exponential, and we are just left with x equals natural log of 7.5. All right, if we put this into our calculator to compute this, what I get is x equals 2.015, rounded to the nearest thousandth. All right, that's about as close as we can get visually when we look at our graph. That is approximately 2.015, and so this is what we can do with these ones. All right, the next thing that we're going to do is we are going to apply these techniques to exponential equations. All right, so let's see here. If we look at our first example, we have the numbers of Western Atlantic bluefin tuna has declined exponentially. Their numbers in thousands can be modeled by the formula f of x equals 230 times 0.881 raised to the x. And we have x is the years after 1994. All right, we want to go ahead and start by estimating the number of bluefin tuna in 1974. All right, so 1974, if we come back and we look at our statement here, x is the years after 1974. So 1974 is actually x equals 0. This is our starting year. And so remember, when we first talked about exponential functions, remember that we had that the number with the exponent, we called it our base multiplier, and the number outside was our initial value. And so for this one, we actually don't need to do any work. We just want that first number. So in 1974, there were 230,000. Remember that we did say that this was in thousands. Tuna. We can also write this, instead of in words, 230,000, we can write this as 230,000 using just digits. Okay, so no work for that one. All right, the next one we do have to do a little bit of work. It says estimate the number of bluefin tuna in 1991. And so the first thing that we want is we need to figure out what is x. So we're going to go 1991 minus 1974. And I believe this is going to be 27. It is not. I can't do math. This is 17. All right. Okay. All right. This is just going to be a calculator problem. It is an x value. And so we want to plug in 17 for x. But this isn't anything that we can do by hand. And so we use our calculator. We're going to plug this in. We get 230 times 0.881 raised to the 17th. And what I come up with is 26.69. I don't know what we're supposed to be rounding to. But what we should have, let's go ahead and say this is approximately 27,000. And of course, when you're doing your homework, make sure that you do pay attention to what it wants in terms of rounding and in terms of, do we want to write it in digits or can we just add the word thousand? All right, the last one's going to be the one that actually requires the work. So it says, determine the year when it is expected that there were 50,000 bluefin tuna. And so this one, what we have is, this is not a year, this is not an X value. We want to plug it in on the other side. And so what we get is 50 equals 230 times 0.881 raised to the X. All right, so now we're going to use our techniques that we've been working on. We want to solve. The first thing that we want to do is isolate our exponential. And so we want to divide by 230. I'm just going to simplify that a little bit. I'm going to make this 5 over 23. And this is equal to 0.881 raised to the X. From there, we can take log of both sides, and again, it doesn't matter what log we use. But what this allows us to do is to take the X and move it to the front. Finally, we can go ahead and divide by the log of 0.881 to both sides, because it is just a number. And this is now a calculator problem. And so if we put this into our calculator, we get log of 5 divided by 23 divided by log of 0.881. I get 12.044. This is a year. Remember that we want to determine the year. And so this is going to be 12 years after 1974. Remember that was our starting year. And so this is going to be in 1986 will be our final answer. All right, so notice that even when we don't have nice numbers, we can still use the same techniques that we talked about previously to solve application problems. All right, we got a couple more, so let's go look at those. All right, the second one we have is the population P in billions of the world was 7 billion in 2011 and can be modeled by the function P of X equals 7 times 1.01 raised to the X minus 2011, where X is the year. Not the year after 2011, but the actual year. Okay, so this problem is asking us to determine when the population is expected to reach 8 billion. All right, so this is not an X value. We are being asked when will this happen. And so our 8, we are going to plug it in for our P of X. And we want to go ahead and solve. I want to isolate my exponential. So I'm going to start by dividing by 7. We get 8 divided by 7 equals 1.01 raised to the x minus 2011. We can take the log of both sides. We get log of 8/7. We can move our exponent down to the front. We get x minus 2011 times log of 1.01. And again, from here we can do a couple different things. If you want to avoid really nasty fractions, we can go ahead and divide by log of 1.01. And what we get is x minus 2011 equals log of 8/7 divided by log of 1.01. We can add 2011 to both sides. And it's not letting me do it. All right, let me try that again. I don't know what I did. All right, we add 2011 to both sides. And what we get is x equals log of 8/7 divided by log of 1.01. And then we want to add 2011 onto the end of that. All right, so when we do this, we get I get 2024. Of course, this problem didn't take into account COVID, but they didn't know that was going to happen. All right. Okay, so this is the second one that we have. All right, the last example that we want to look at is we have determine how long it will take an amount of money to triple if it is invested at 9% compounded quarterly. All right, we're going to bring back in our compound interest formula. And so remember that our compound interest formula was A equals P times 1 plus R over N raised to the NT. We're going to plug in what we know. The first thing that we know is we know that R is our rate, and it's going to be 0.09. And we know that quarterly means that this is happening 4 times per year. And so I can replace my N with 4. Now the problem is here it doesn't tell us what the principal is, which is usually what we want. But we do have something here. We said it asks us how long will it take an amount of money to triple. And so you can go ahead and pick whatever amount you want to invest. Okay, let's just say that we're investing $10. Okay. If this amount triples, it turns into 30. And it doesn't matter what number we pick to start off with. The first thing that we have to do on this is we need to isolate our exponential. So I'm going to go ahead and divide both sides by 10. And depending on what amount you pick, you're going to be dividing by a different number if you pick something else. But basically, all of us, as soon as we divide our A by the P, we should all have 3. All right, the other thing that I want to do is I do want to simplify that inside number just a little bit and make it a little bit easier to work with. If we divide 0.09 by 4 and add the result onto 1, we should get 1.0225 raised to the 4t. All right, this is now just a regular exponential function. And so we're going to do exactly what we've done before. We want to take the logarithm of both sides. We can move our exponent over to the front. And one of the things that I do want to point out now is on the right side, we have 4 times t times log of 1.025. And in order to get t by itself, well, we need to divide by the 4. We also need to divide by the log of 1.0225. And so that's what we're going to do. We are going to divide both sides by 4 log of 1.0225. And again, when you put this in your calculator, make sure that you do have that in parentheses. All right, if we do this, I get t is 12.344, and so we're going to say 12 years. Again, depending on how they want it rounded. All right, that takes care of our application problems. And this finishes up our discussion on solving exponential equations. In the next video, we are going to talk about solving logarithmic equations. And so I will see you again shortly in order to finish all of this up. Thank you.